All right, welcome to the ME 3035 lecture for September 27th, 2019. I am going to be using a couple of tools, one of them of which is Photoshop to make some drawings, and I'm also going to be using the text tool, so you may hear some clicking as well from my keyboard, but primarily I'll be using the brush tool and then having some audio above what I'm drawing and doing. In addition, there will be a few times where I will either speed up the video or I will have little breaks to go off and pull out a particular image that I want to use for some of the examples. So at certain times, there may be an opportunity for you to skip or scrub through the video and watch a drawing appear before your eyes very quickly so that you can save some time. In addition, of course, you can play the video at 2x speed or 3x speed or even slower if you want. I'll try to speak relatively slowly, but there will come a time, of course, when I might default back to my normal speed at some point during this lecture. So without further ado, let's start jumping into the content, and hopefully you're all ready to enjoy a lecture on video. The first thing that I just kind of want to remind ourselves is that we have some sort of problem statement. And this itself is effectively the problem that we are trying to solve. We are trying to identify the model and the solution of the prediction of some sort of mechanical system, part, component, what have you. And as you recall, we spent a lot of time talking about, well, what do we do? And we usually go to some sort of free body diagram. Right here, and there's a process, and it's the first two steps in that 5-step process of solving these problems. And we keep on going through that process, and I'll do one more step right here, and then I'll mention that we need the equations of motion. And this is kind of where we've stopped so far in the class. But eventually, if we want to start to solve these, we need to take it to the next step. And so I'll do another little arrow here, and I'll say that this state variable form is where we need to go next, because if we want to solve these things numerically, well, we need to have a certain state variable form. All right, and then we would do this using a couple of tools. One of them was Euler's method. Another one was Hoyne's method and RK4 methods. And one of those RK4 methods effectively was this thing called OD45 in MATLAB. And we'll talk about those in a few minutes after we go through this process. All right, so let's start with a little example that you've seen before, and I'll spend some time drawing it, but of course I'll try to speed this segment up. All right, well, you've seen something like this many times, but we'll start right here just to remind ourselves how we try to go from a free body diagram here to an equation of motion. So I'm going to spend some time now and quickly whip up the free body diagram, and then we'll also do the equations of motion. All right, now we've got this equation of motion, and we need to start thinking about, well, if we recall from up here, right, how do I go from the equation of motion to a state variable form? Well, the state variable form has a special form as expected, and in particular, it's like this. Okay, so what does this mean? This means that we need to have all of our states, the things that we're tracking, the things we care about, the variables of interest on the left-hand side with a single derivative, and these single derivatives are going to be functions of the states themselves, okay, without the dot, without the derivative, and a whole bunch of other things. This u represents, for example, this stuff right here, maybe external forces. It represents this stuff right here, parameters such as m and k in this example, and all the things that are going to be constant throughout the whole simulation or the whole solution. Now, this x right here and this x right here could actually be a vector. So I'm going to put a little line on top of them to make it more explicit, to represent the fact that this is actually a state vector. So we're going to define a state vector right here. Okay, so x is a state vector. There's our state vector, and then of course we're going to have the state derivative. You'll notice then that everything in the state derivative is just the derivation of the state vector element. So I'll go do one more step here, and then I'll label these things. All right, so again, we've got this state vector right here. And of course, a vector can be composed of one, two, or more elements. And then we've got our state derivatives right here. Okay, and of course, we represent these differentials with a dot on top right here, right here, right here, and so on and so forth. All right, so that kind of takes care of what this term is right here and what this term is right here. And now what we need to do is take our equations of motion and try to put it into the state variable form. So we're going to come back over here, and what we're going to first do is isolate the highest order term. All right, so now we've isolated x double dot, but the problem though, of course, is this right here is a second order system. Okay. So what we need to do is, if we want to solve this numerically, we need to somehow replace, okay, this guy right here into some sort of first derivative. So let's try to do that. Well, we know that we can substitute velocity for x dot. So let's say that x dot is equal to velocity. And of course, if we take the first derivative of this equation right here on both sides, we're then left with x double dot v dot. So what we can do then is replace this x double dot with this v dot. So let's do that right now. All right, so this looks pretty good. And now what we have is that we have a first order ODE but there was 2 degrees of motion. Okay, if you recall, we have the motion, or the sorry, there wasn't 2 degrees of motion. There's only 1 degree of freedom. Okay, but energy, of course, can be stored in 2 ways, and that helps us identify, okay, the other first order ODE, which is this guy right here. So as a result, what we can take a look at is we've got this right here is a variable of interest, and this is a variable of interest. Why is that? Well, because energy can be stored in the spring, and so we want to know what x is at all time. And energy can be stored in the motion, or in the velocity of the mass, and so velocity is important over all time. Except we don't have x and v at all time, we have the first derivative. So what we can do then is set up our state vector. And of course, we can set up our state derivative. And now we can put our system into, well, state variable form. And of course, we can, following this pattern right here, set up our state variable form. So now we have the state derivative on the left-hand side, and it's going to be a function of all of these things right here. Okay, and in particular, okay, we can solve for these independently by making it this way. So what do we have here? Well, we have two first order ODEs and that allows us to solve it using, well, various numerical solvers. Okay, so the next thing we're going to do is talk about how we can take this state variable form and place it into some sort of numerical solvers, and we'll start with Euler's method. So if you recall Euler's method, what we did is that we had some sort of variable of interest. Let's say we care about x for all time. Well, we didn't know what x was going to be. Okay, but we might have known what x is currently, xi. And then what we did is that we added, okay, some sort of derivative information. I'll call it dx. Times a little bit of t, and that allowed us to march forward in time and get x at all points. So effectively what we did is that we had xt at, say, time 0. I'll just do a little dot right here. Then we went into the future, delta x, we knew what it was then at x at that time, and then later on, and then later on, and then later on. And then eventually we would link these guys together so that we would have a profile of xt at all times. We do the same thing for the velocity. And same sort of process. Those are linked. All right. Now, of course, we can see, let's just maybe make this different color. We can see that this guy right here, okay, if I link up right here, is very similar to this guy right here. And this guy right here is nothing more than the time derivative of velocity. Okay, so then what I can do is that I can replace those v dots. I'll just make some copies right here. All right, and then I made some copies, and now I'm going to go in and I'm going to replace, okay, this guy and this guy with those functions. So now what I can do is I can replace this guy with a function. Okay, and I'll come up here and I'll replace him with some function, okay, that uses the state vector and a bunch of other things. Okay, and I'll call it function 1. And I'm going to do the same thing for this guy right here. I'll call it function 2. And where are these functions? Well, these functions are exactly what's on the right-hand side of this state variable form. So I'll do this one more time. And now I'm going to replace these guys with the specific functions themselves. Let's go back up and look at it then. So we have x dot, which is v. So this whole function is going to be v. And this guy right here is going to be this equation right here. Now we have all the parts and pieces to extract out these profiles, and we can solve numerically what v is at all time and what x is at all time. And this is Euler's method. I'm now going to go off and try to find a little summary chart so you can kind of see what's going on with it. Okay, there's a few things that you should notice then, that because we need to have everything on the right hand side be current states, we need to come in here and add a little I right here. And then of course on this one we need to add a little I on this one right here. Okay, and this is effectively what Euler's method does to numerically solve. So now let's go off to MATLAB and we'll try to code this up and then take a look at some of these figures. Okay, here we are in MATLAB. You'll notice then that I've already got a script open called Lecture September 2019. It's a .m file. You can see I've got my command window right here. My workspace, I should clear all my workspace and I'll clear my command. Whoops. CLC. And what I normally do, in fact, is I clear my workspace and my command window often at the beginning of my script. So I'll do clear all and CLC. And I also like to add close all in case I have any figures that are open. All right, well, I'm going to start by typing in what I had before for the Euler method. And if you recall, I had two equations of motion that were useful for tracking out what x was. And so I'll do x I plus 1. This is, of course, the subscript for the time of I plus 1. And it's going to be equal to the current time that I have, okay, at xi, plus some sort of dx dt. Okay, there's a slope there. All right, and it's also at a specific time, so I'm going to add I right there, and I have to multiply that by my dt, or my time step. Okay, I'm going to copy and paste this for my velocity because it's very similar, with the exception that I have to change the x's to v's. okay, in all cases. And now I need to kind of take a look at what these are, because these are going to be defined before I use them. So I'll have dx dt of I, okay, and I have dv dt of I, okay, and these are actually going to be functions. As we discussed, those are going to be the equations of motion, where the left-hand side is going to be the first derivative, and the right-hand side is going to be a function of the state variables and parameters and constants and external forces, like we talked about in class on Wednesday, and also before when I was showing some of those examples in Photoshop. Well, if you recall what these are, dx dt is pretty easy. It's going to be nothing more than the velocity state, and in fact a velocity state at a particular time, vi. The dv dt is a little bit more complicated, okay, because dv dt of course is an acceleration to some degree, okay. So if you recall from the equation before, it was a force divided by the mass minus k divided by the mass times, well, the position that the spring had compressed or was stretched, x, and it's not just any x, it's actually x at that particular time of I. Okay, so these then are kind of the key parts of Euler's method, where effectively we have some functions right here that go into dx dt and dv dt, and of course we could call those f1 and f2 or whatever we wanted to do it. But we need to put this process or this sequence of 4 lines inside a for loop, because we're going to iterate. Okay, so we're going to iterate from time or unit 1 all the way up to, well, something else. I'll leave it as 10 right now. Okay, but effectively this means that we're going to iterate through Euler's method 10 times. I'll come back and end it right here, and I'll tab over just to make it look nice syntactically. All right, and now we can see there's a whole bunch of little squigglies right here, so we need to kind of define some of these things, or else we're going to get a whole bunch of errors. Okay, one of the first things, of course, is that it's going to go from right to left, and so we need to have v defined, okay, when I is equal to 1, or else this is going to give you a problem. If not, let me show you. I'll hit run right here. Okay, we see it, yeah, undefined function or variable v. So we'll come in here and we'll define v at the first time step, which is actually when time is equal to 0, and we're assuming then that the block is not going to move at all, or its speed, its velocity is 0. Okay. We also have some problems later on about x, so I'll put x up here, of course, at the first time step, okay, which is actually a time equals to 0. We'll say that the position is also 0, and that's of course that static equilibrium. We assume then that our position coordinates are positioned such that when the time starts, or the simulation or the model starts, we have 0 displacement. Okay, then there's a few more things that are going to give us some problem. Of course, we need to define the mass. Okay, and so maybe we could say that the mass is 100 kilograms. Keep everything in the SI units. We're going to have some sort of spring constant. Maybe we'll make it quite large initially, so we can kind of explore if 200 is large or not. Okay, Newton meters. And then we will also have an external force, and we'll keep that to be 40. All right, and so we're defining all these different terms. Okay, and now let's first of all see what happens when I hit go. There's still an error that hopefully you can kind of recognize. Looks like we got through the dx dt part, we got through the dv dt part, and now we have another undefined variable dt. Ah, well, that's just our time step. We can set that to usually something small, okay, but I'll just start here at 0.1. Okay, the units of that, of course, are going to be seconds. And then I can try it again, and it looks like I'm starting to get something out. Okay, but here is something that you need to be aware of, is that I'm not really stepping through 10 seconds. I'm going to be stepping through 10 iterations of this process, okay, which means that since I'm having 10 time steps, I really am only going through 1 second. So what would be nice then is for me to kind of control the start time and the end time for my simulation, and then of course just use I to iterate through those times. So it's also quite often useful to have some sort of t initial, okay, and that's going to be 0 usually. there's going to be t final. Let's say that is actually 10 seconds. Okay, and then I can make some sort of time vector that spans t initial to t final. Now, you may remember from your 273 days that if I don't have any sort of second colon in between, that this right here, if I come over here, I'll pop it down. Okay, it's going to result in t as a row vector from 0 to 10 with the increment of 1 by default. But if I add dt in between and add another colon, I can come in here and take a look down at the bottom right. I can see then that all of my increments are going to be 0.1, 0 to 0.1, to 0.2, to 0.3, so on and so forth, all the way to 10. And that results in a row vector of 101 different elements. Which means then that I need to iterate from 1 to 101. Okay, but because I don't want to have to change this all the time, I'm going to go in here and say I want to go from 1 to the length of my time vector. Alright, so let's see if this works now. I'll hit run. Looks like I've got a bunch of things that are not suppressed right here, but for the time being I can use it because I can see then that I actually have a row vector for v, okay, and a row vector right here for x of 102. So I have one more than I need, and I'll do this, minus 1. And why is that? Well, because this last guy right here is going to go to the end and then add one more, so I want to stop at 1 before the end, the penultimate element inside these vectors. Alright, so let's run this again here. Looks like now I've got 101 elements for v, 101 elements for x. Why don't I try to plot it? So I'll go into a figure, and I'll do a simple plot. And I want the time vector versus, say, the position. All right, so let's go up and we'll plot this. And so here is our first output for this spring system, and there are some interesting things that we should notice. First of all, it looks like it's increasing in amplitude over time. So you should ask yourself, what is the cause of this? Let's first of all see how big it gets when we increase the amount of time. So we'll make t final by 20. I'll hit run. And it looks like this spring is slowly increasing. It looks like it's very unstable and it's gaining, right, in amplitude in terms of displacement. Well, this is not necessarily a problem with the physics. We actually need to take a look at our time step. If you recall from ME 273, they talked about how if you implement Eulers, you need to really make sure that you have a small enough time step, or else there's going to be some instabilities and some convergence problems. So let's go back and we'll actually change our dt to be 1/10 as large. Okay, and I'll hit run here again. And now that the time step is much smaller, we can see that there's a lot more output on the command window. So we're going to go back and suppress a lot of these things so that we don't have to see them as much as often. In fact, I'm going to even kill it right now with Control C. I'm going to suppress all these things and everything will work a lot faster. I'll come back in and hit go. All right, and so we're doing a lot better. Although we can see that there is some still interesting things here. In particular, right, is it still getting more and more unstable, or is that something else? And so we're going to explore that a little bit later on. But for the time being, now we need to kind of label these things. So we're going to go back into the figure and we'll do an X label. We'll add it, oops, not time, but in position. Okay. Actually, no, that was right. Sorry, X is going to be time. Y is going to be position. Okay. And since I actually have more than one state variable, I don't only have just X, but I also have V, so I'm going to make a subplot within this figure. Okay, it's going to be 2 by 1, and I'm going to talk about the first one first. And then I'm going to do the second one on the bottom right here, and it's going to be with respect to V, and it's going to be velocity right here. Alright, so now let's run this again. Okay, so now I have some sort of spring, and it's moving over time. It's oscillating back and forth, and I do need to kind of take a look at why is it slightly increasing. Okay, so there might be some other almost instability problems there. We can experiment it with a little bit more by dividing by 10 the step size. Let's see if that helps a little bit. Okay, Looks like it's pretty good based on the 20 seconds. Okay, so a little lesson there, or to remind you of Euler's method has some challenges, which is why we're about to go to ODE45, which is a higher order method and can account for much better accuracy even if the time step is rather large. To play with this a little bit more, we're just going to increase the mass, okay, by 2. Let's take a look at what happens. Okay, did it go up or down? Right, we can kind of play with these things if we do hold on, right? So I'm going to come back here and I'll do some hold ons after we plot it. I'll actually turn off the close all. So let's run this one more time. So there's figure 1, and then if I decrease the mass down to 100 kilograms again, all right, we can start to see the differences. Okay, so the red one is the 100 kilogram one, the blue one was 200, and so you can start to see what does mass do. Increase mass, does it delay the oscillations? Does it increase the amplitude? We'll explore this more so, but of course there's impact from mass on the position and on the velocity. Okay, I'll do one more. In this case, we'll actually make the constant much higher, the spring constant much higher. Okay, and so now in this case we have a little yellow one right here. Okay, the last thing I'm going to do is this position isn't oscillating around 0, but it's always positive, okay, with respect to that static equilibrium point. Okay, which means then that the static equilibrium point might be somewhere in the middle right here. Okay, so what we're going to do is that we're going to turn off the force. So if I is less than, let's say, 5,000, or rather greater than 5,000, set F to be 0. Effectively turn off the force. Okay, and let's see what happens there. Why do I choose 5,000? Well, because my time step is 1/1000th, and so this would equal to when the time is greater than 5 seconds, I turn the force off. All right. So does it do anything right here? Well, I've actually made a mistake because t, right, is not related to this. I need to make I greater than 5,000. So there we go. That's what I wanted to show you. In this case now, after 5 seconds, we turn off the force, and so there's going to be a new static equilibrium. Now, why is that? Well, think of this force as kind of like a gravity that's always there all the time. So as a result, the static equilibrium is going to balance out that gravitational force. But if you remove gravity, you don't need to have any sort of delta for that spring constant, and so you're going to have a different position for your static equilibrium. We'll talk more about this later, but I just want you to kind of see that you can play with your homework assignments to try to learn a little bit about the impact of all these different values on the dynamics of various systems. So what we're going to do is we're going to come in here and we're going to label this one Euler's method, because that's what it was. We're going to come down here and we're going to perform the ODE45 method. Okay. Now the ODE45 method is similar to Euler's method in the sense that there's going to be some sort of time vector, okay, some sort of time span in which we care about. There's going to be initial conditions right here, and then there's going to be some functions. There's going to be some sort of x dot or derivative functions for our state variables, x and v. Okay, so here's what we're going to do. We're going to go off and we're going to do a help for ODE45. Okay, and we'll take a look at the very top right here, and it says, if you can read it, this ODE45 integrates a system of differential equations. Okay, these y primes. Okay, these are these functions right here that we talked about in the examples from time t0 to t final with initial conditions y0. Well, it sounds like that's exactly what we're doing. So we're going to come in here and we'll dial in and copy and paste this one right here, and let's talk about these things. So up here in Euler's method, we had these little functions right here. Okay, and of course you could replace these with, say, f1 and f2. Okay, and I'll replace them right here, f1 and f2. Effectively, all they are functions, okay, that provide equations for the state derivatives. Okay, so I'll go back here to the Photoshop, and if you recall, all right, we have these little functions right here. Okay, one of them is, of course, v, The other one is a little bit lengthier right here. But this is how we broke up the second order ODE into two first order ODEs. And of course we have a state derivative right here, which means then that the state derivative is nothing more than functions of those state vectors and forces and masses and other things like that. So then we can use, okay, this state variable form to solve numerically these problems. So what do we have for these functions are contained in ODE fun, or ODE function. Right? So what I'm going to do is I'm going to go off and first of all make those functions. Okay? So it's a function. Okay, and what does it do? Well, it's actually x dot. Where does that x dot come from? Let me go back to your Photoshop here for a second. Okay, it's this guy right here. For the state variable form, we're going to have some sort of function that returns to ODE45 a vector, okay, of the first derivatives of our state vector, and that's why we get these state derivatives right here. Okay, so coming back to our function, so x dot is going to equal to, well, let's call equations of motion. Okay, simple. Okay, and of course it's going to take in time because that's important, and our x, or our state vector. Okay, so well, how many state derivatives are there? Well, there's the same number as there are elements in the state vector. So we'll do x dot equals, to initialize it, zeros, okay, the length of x, and of course 1. Now that I've got x dot, I can start to fill them in. So there's going to be two of these guys. There's the first one, and it's going to be a function, and there's a second one, and it's going to be a function over here. Just like in the Euler case right here, I'm going to have two functions, okay, that are going to replace this section right here and this section right here. Okay, but I'm going to use OD45 and a function to link it, okay, to, instead of this whole for loop, I can do it in one line of OD45. Right? So coming back here, I know that my first function, right here, is nothing more than my second state, this v right here. Okay, well, my second state, okay, if I come over here again, was this guy right here, or rather right here. So I can come up here and say that x dot 1 is actually x2. Okay, in other words, that the time derivative of x, the position coordinate, is just the velocity, which is found in the second element of this state vector right here. Okay, for x dot 2, the second element of my state derivatives have, well, a different function. There's f divided by m minus k divided by m times, well, x position, which is going to be x of the first one. Okay, coming back to Photoshop right here, it's going to be this guy, okay, but without the dot. Effectively the first element in my state vector. All right, so I've got these two functions. And you'll notice then that they're eerily similar to these guys right here, because that's all the Euler's method to the OD45 method requires. Okay, I now set up my vector of slopes, or my vector of time derivatives, which is nothing more than having some sort of vector of f1 and f2. Okay, and then I need to define some of these variables. So I'll grab them from right here. M, K, and F are now defined. And then what I can do is I can link this set of functions, okay, there's two of them right here, to OD45. And I can do single quotes, which is one way to do it. All right, it calls it out a little bit better. And all I have to do then is save this file called equations of motion simple. So I'll come back here and I'll save it. All right, I'll save, it's already by default equations of motion. Okay, and now I can go off and see if this works. The first thing I'm going to do though is I'm going to comment out all of Euler's method, and for the time being I'm going to comment out all of these figures and just focus on this top part right here. Now, t-span, right, is going to be something very similar to t. So I'll come in here and I can just either, well, I can leave it as t right here, or I can call t-span up here. I'll just put t down here. And then y0, okay, are my initial conditions. Okay, it's going to be a vector, and I have, well, x1 on the top side and v on the bottom side. So now what I have is, based upon my Euler method, I have my initial conditions, I have my time vector, and I've got my slopes, or I've got my functions, which means that I've got all these parts right here on the right hand side for the Euler method. But now I can use OD45, which will take care of all this for me in a very creative, more accurate way. And we'll talk about that later on. So let's see if this works. Okay, I hit go. Looks like MATLAB spit out some things for me, but let's see what it is that it spit it out. So I'm going to scroll back up from the far right here, and looks like there's a lot of data, but it looks like it spit out something called y out. That's good. And I'm going to keep on going. It looks like it spit out something that looks very sequential. Oh, t out. Okay, so what does it spit out? Well, OD45 is going to spit out two things. Okay, very similar to Euler's method. First of all, it's going to spit out the time. Okay, and not surprisingly, it's going to match t. Okay, because I specified it directly. There's other things you can do so that this might not match it. So, for example, you can actually just give t initial and t final. We'll do that a little later on. Okay, and then we'll take a look at t out. And you also have an output of y out. Okay, and it has, well, what does it have? It's got two columns right here. Okay. Now, based upon our input y, or our input initial conditions, okay, the first column is going to be our position right here, and our second column is going to be velocity. Okay, so let's take a look at this. Let's see if it ever goes negative. Oh, it looks like right here, okay, velocity, the second column goes negative. Okay, and then down here, it looks like it goes negative again, and it looks like it goes negative here. And it looks like, based upon what I'm looking on the first column, that this guy never ever goes negative. So let's go see what happens then here. We'll turn our figure no longer hidden. Okay, and because we have t and x right here, we need to kind of massage some things. Effectively, x at this spot is going to be y out. Okay, it's going to be all rows, and it's going to be the first column. Whoops, there needs to be a round bracket right there. Okay, our time is just time, but our v in this domain is going to be, well, all rows, but the second column right there. All right, so let's spit this out. Okay, and now we've got something interesting right here. Okay, so we have position of 0. Okay, and it comes back to that 0 point right there, and it appears that we have some sort of, well, stable system. Now, this is not what we saw with Euler's. So what do you think the problem is? Well, the problem is that Euler's is not as accurate. So let me explain. In ME 273, we talked a little bit about these time steps, and now you decrease the time step, you can get closer and closer to the actual result with Euler's. Let's go back to Euler's and see if we can fix it up now. I'm going to take this off right here. Whoops, other way. Okay, I'm going to suppress both of these guys, so we don't have to look at them when they pop up on the command window. For the time being now, I'm going to comment out OD45, and then I'm going to make my dt much smaller. And let's see how it performs. Let's see if I can, yep, 100, 280, 100, 280. Let's see how it runs now. Ah, so we're doing much better. Okay, and this is what we expect with the spring. So all that instability was not necessarily an instability with respect to the system, but it was an unstable selection of our dt. So the power of OD45 is that even if you choose a large DT or a large step size, it can still do pretty good because it uses fourth or fifth order tools to effectively predict the best slope for these functions right here. All right, so what should we do here? Well, let's take a look at this. Okay, now that my DT is small enough, okay, this spring is activated right at the beginning with a force, then it gets turned off at 5, and then there's no other sort of forces. If I take away now this turning off of the force, okay, we'll notice then that now the position is always positive, like we saw in the OD45 case. Okay, and its displacement is varying over time. And as expected now, that potential point right here, when it's maximum potential, usually, well, now it'll be linked with 0 velocity because all the kinetic energy is gone and there's only potential energy in the system, whereas a little bit later on, down here, it's all kinetic energy, approximately. And very little kinetic energy. All right, so the main advantage of OD45 is not only is it usually simpler to code up, so for example, this is 3 lines instead of, a whole bunch of lines right here, but it also is more accurate at smaller step sizes. And on top of that, you can have interesting things be performed because it's adaptive. You can set T initial right here and T final right here, and it will choose different time steps for you. So let me comment out Euler's method right here. Okay, then I will turn on or run. Whoops. I need to change T now, okay, to T out. Why is that? Well, because T right now is still 201. Effectively, it's this time value right here, but I want to use T out for my comparisons. Okay, you can see then that I have the same sort of result from beforehand, but let's go to my workspace and take a look at T, and it's actually 165 doubles right here. Okay, you'll notice then that the time steps in between each one of these times is different. Okay, they jump around, they start actually quite small, and then they get bigger and bigger to the point where it's not always 0.1, but sometimes it's 0.1, sometimes it's 0.2, sometimes it's much smaller. But the only thing that I've defined is effectively the end point and the beginning point, and so that's another advantage of using OD45. Okay, so there's our first example of OD45. Let's go back to Photoshop. We'll talk a little bit about how OD45 works, and we'll talk about a few more examples. So I've gone through and I've added, of course, Euler's method right here. Okay, and Hoyne's method is very similar to it in the sense that we have the same sort of process where we start off with an Euler step. Effectively, we have some sort of function that we multiply by delta t to get a prediction of the next time step. But then we use that time step down here and we average them together to get hopefully a better slope predictive step. So essentially what these arrows indicate right here is that you have one slope right here, okay, as predicted by this function right here, the time derivative from your state derivatives. You go forward in time and you find out what the next slope is, or what it would be. Then you average those two together, and collectively then you finally take your step. So what it is just kind of like a weighted average of these time derivatives. Okay, remember these functions are nothing more than equations that represent some sort of slope or time derivative of one of your state variables. Well, if 2 is better than 1, from Hoyne's method to Euler's method, well, you can do Runge-Kutta methods, fourth order, and you do the same sort of thing right here. In the sense that you can have K1, K2, K3, and K4 all represent different slopes at different points in time that are dependent upon each other. And then you do a weighted average of all 4 of those. Okay, 1/6 plus 1/3 plus 1/3 plus 1/6 times delta t. And that's going to give you a much better way for predicting the actual next step for your state variable. Okay, this process then is effectively followed by OD45 in MATLAB. But it's essentially the same thing. It's just a more intense sort of way of figuring out what that function is all about. And if you recall, back in MATLAB, okay, we have this, okay, as the default, but then it's going to do this 3 or 4 times to make sure that we actually have a really good slope, so that then when we take that step, we can get the next value out from for our state vector. Okay, well, all of that is great, but it's always nice to kind of see another example. So I'm going to go off and I'm going to make another one, but all it's going to be is a slight modification of the one that we just saw. Here it is. All right, and now I'm going to write the equations of motion. All right, and now since it's a second order system, we need to isolate the highest order term. Oops. We need to use substitution to bring this guy down to a first derivative. And I will cheat and just make this copy right here. And of course, then we have the other derivative right here, which is going to be x dot equals v. So again, our state vector is going to be xv. We'll have our state derivative be x, this guy. And then, of course, we're going to have our equations of motion be this. And in fact, I'll just come in here and copy it out. And this right here then state derivatives. This whole thing right here is our state variable form. All right, well, we can pretty much use the same code. So let's go back, okay, to MATLAB, and we'll add in this one extra term right here. We use the same mass, we use the same spring constant. We'll add in a damping factor, okay, and we'll just set that to be, let's say, 1 right now. Then we'll come down here, right, and we're no longer going to mess with Euler's method. Okay, so I have to come in here and add in that b. Okay, effectively I can just copy and paste this right here. Okay, and then I can add one more value right here, minus b times, well, x, which one should I add? Well, if I come back, it's going to be x dot. But x dot itself is actually this guy, which is also this guy right here. Okay, so of course I can replace this, and I'm going to do that right now. With v. Okay, so everything on the right hand side has to be state variables from my state vector, has to be constants or parameters that are known, or inputs of some sort. Nothing on the right hand side then can effectively have derivatives. Okay, so if you have any dots on the right hand side in your state variable form, you need to replace them. So now what I can do is I can replace this guy with what I already had for that first vector, or that first function, which is this one right here, x2. I'm going to multiply that together. Okay, and I also have to have that divide by m thing, because that is expressed across the entire variable. All right, so I've updated now my equations of motion. I'm ready to go back and run OD45. I'll hit go. Okay, and it looks like there's a little bit of damping because that new red line, okay, is slightly smaller than the other line. Let me try to stretch this out a little bit and see if I can see any more. I'm going to do 40 seconds now. Okay, we can see that there's a little bit of damping going on past that 20 seconds. Okay, I'll stop it here. And what I'm going to do is I'm going to up my damping to be 10 times stronger. All right, so now what we see is that based upon what I have for my inputs, okay, there's going to be some sort of damping of the signal, and eventually it's going to reach a steady state if I let it go long enough. Effectively, it means that if I'm pushing on this mass long enough with damping and with the spring constant, I might reach a new point of static equilibrium. So let's take a look at how this works. Well, effectively, I start with some force that's going to cause the mass to move. It's going to cause the mass to move at a velocity, and as a result, I'm going to trade back and forth kinetic energy and potential energy the whole time, except that that kinetic energy, that V, is going to be damped out regardless of which direction it is. So when the velocity is positive, okay, damping is going to push it back to 0. When the velocity is negative, damping is going to pull it the other direction, but it's always going to oppose the direction of velocity. All right, now this idea right here from Euler's method is that we turned off that force when the time was greater than 50. We can do the same sort of thing in our equations of motion right here. So effectively, we can say, well, if our time is greater than 5, we can set F equal to 0. Effectively, it means then that the force is going to be pushing against this mass for the first 5 seconds, and then it's going to be turned off from time 5 to time 20 seconds. Let's see how it adjusts things. All right, so this is interesting. Okay, we have some sort of force which is pushing it to some sort of new static equilibrium, which is going to be to the right of what that initial 0 point was. But after we turn it off, okay, we just left the spring to its own by itself, and the spring and the damper are going to work in concert to slowly dampen out the oscillations of the spring. Okay, you know, the same sort of thing with the velocity, where it's following a trajectory, and then of course when we turn it off, okay, the velocity is going to slow down over time, and eventually it's going to reach 0 velocity at that static equilibrium point of 0 again. All right, so let's increase it even more, okay, and we'll see if that impacts it. Whoops. Oh, I should mention, of course, that if you change, right, these constant terms in your main and what's more important, though, is that I should change it in my equations of motion. So I'll come over to here and make this to be even bigger. Okay, we see the damping is even increased. Let's do it one more time. I'll double it again. Okay, and there we've got this weird sort of behavior, but I know what the position of this mass is for all time based upon my initial conditions, my forces, and all my constants, namely m, k, and b. All right, well, let's go try more complicated ones, because we have more than just 2 degree of freedom sort of systems right here. In fact, this is a 1 degree of freedom system. Okay, well, we're going to come up with another example here. And I'll start drawing it out, and I'll accelerate the video, and then I'll probably jump right to the equations of motion much more quickly. Okay, you might remember this from your first homework. And what I'm going to do now is just extract out the solutions that you have still available to yourself. So the first step, of course, to convert this system of two second order ODEs to a bunch more first order ODEs is isolating the highest order term. So we're going to do that right now. And we take a look at x double dot, that comes from right here. Okay, and of course we're going to divide out the M1. Okay, and then everything is going to come to the other side. So we're going to do minus, I'm going to change that B to a C right now. So let me just come in here and make that into a little B. Hopefully that's okay. We have x1 dot minus k1. Maybe I should show you what it is here before. k1 x1. Oops. That's going to be a negative. Okay, we're effectively bringing everything over to the other side, and then we're isolating M1. Of course, we know that we have x, well, I should add 1 right here, x1 equals v1. Okay, and then of course we're going to substitute this equation into this guy, so we're going to have v1, okay, equal to this whole equality over here. I'm going to cheat and grab a bunch of it. All right, and then I'm going to come in here and we are going to replace this guy, okay, with this guy right here. So I'll come in here and erase him, and I'll come back here and add v1. And now we have two equations. They're both first order ordinary differential equations. And we're ready to move on to the next one. Okay, well, the same sort of thing. We've got x2 double dot. It's going to be 1 over m2. And then all this other stuff right here. So we're going to have ft. Let's make those a little bit better. Minus k2 x2 minus x1. And same sort of thing then. We're going to come in here and we'll say that x2 dot is equal to v2. And then we can use a replacement to do v2 equals, I'll grab this entire equation, copy and paste it right here. All right, and then we can ask ourselves, well, what are the state variables? Okay, and if you see them, you can see that there are, well, 4 of them. Okay, we've got this guy right here, this guy right here, this guy right here, and this guy right here. So if we were to write out the state vector, okay, we would have x1, v1, x2, v2. Okay, and of course that is the state vector. And then if we did the other one, x1 dot, v1 dot, x2 dot, v2 dot. This is our state derivatives. All right, so now we're ready. Okay, we've put it into state variable form because the left-hand side, of course, has a single dot. It's all a single derivative of our state vector. And everything on the right-hand side is either going to be constant terms, some sort of parameters that we know about. It's going to be elements from the state vector themselves, or our states, and inputs. You can see both on this equation and on this equation, it is the same. All right, well, let's go off to MATLAB. I'm just going to drag this guy over here so we can see him, and I'm going to make this guy a little bit smaller here. Oh. All right, the first thing that we need to do, of course, is update our state vector. Okay, and I'll call this guy here state vector initialization. And maybe we should pull this stuff out. So I'm going to put that down at the bottom in case I want to refer to it later on. Okay, so you notice then that we'll put it in the order of this one. We can have different orders, but we'll do x1, okay, and v1. And then we're going to repeat two more, so we're going to have x2 and v2. Okay, so this is going to be our state vector, and we've initialized it at that first point, and so we need to come up here, okay, and repeat this as well, and have this. I'll reorder it a little bit. We have x1, v1, x2, and v2, and we'll assume that it all starts at steady state, or at that point. I'm going to comment out these values right here because we have these same values in our equations of motion, okay, in those functions on the right-hand side of our state variable form. All right, I'll keep dt as it is, time initial and t final. Okay, so now all we have to do is effectively change our equations of motion so that ODE45 has access to the right-hand side of these four equations. Let's go in there. All right, so this is, of course, all correct. X dot, if you recall, over here is nothing but this one right here. Okay, and we're trying to extract that out to pop it into ODE45. Okay, we need to add two more x dots, so I'll do this guy and this guy, and I'll move those for the time being and call this 3 and 4. Okay, and then we need to talk about these equations. Well, this first one right here, this x1 dot, okay, is definitely equal to this next guy, which means that x2 is going to be the same as the second element in our state vector. Coming back to here, okay, we can see that sure enough v1 is x1 dot, which means that v1 is the same as x1 dot. All right, let's do this one right here while we're here. x2 dot equals to v2, so we can do the same sort of thing for the third element, but in this case we're going to change it to the fourth, which means that v2, okay, is equal to x2 dot. All right, so v2 is equal to x2 dot, which means that the first derivative of the third element is equal to the fourth. Right, so the derivative of the third one is equal to the fourth of our state vector. And now we need to plug in these equations inside our remaining two slots right here. So I'll go 1 over m1, okay, which means we need to come up here and call one of these m1 and one of these m2. I'll make them to be approximately the same, well, I guess double for m2. We need to open up the bracket. We'll go minus b, okay, so b was already set from beforehand at 40 kilograms per second, times v1. Well, what is v1? Well, v1 is the second element inside our state vector. So we need to multiply this by x2. Okay, why is that? Well, this x2 and this x2 are the same, and sure enough, over here we can see that v1 is right here and v1 is right here. All right, now we need to do minus k1, okay, times, well, what's x1? x1 is sure enough just that same value, so I'll come in here and make that into x1. And there's one more term in this equation. Okay, it's minus x2 now, minus k2. All right, so I'll take a moment here and we'll come up and we'll make a k2. Another spring constant, we'll make it a little bit stiffer. We have to make this one to the k1. And then we'll do open and close bracket right here, and then same sort of thing. We've got this guy for x1, okay, minus, and here's the careful part, this x2 right here is actually this one right here, x3. Alright, so this is often where students will make mistakes because they need to recognize that the order of these can be in any order you want, but it's got to refer to the right element inside your state vector. So x3, if you recall, coming back to the state vector initialization, is actually x2. Okay. Alright, we've already done the third equation of motion, so now we're left with this last one. It's going to be very similar. There's going to be a 1 over m2. It's multiplied by f, first of all. And then it's going to be something similar to this guy right here. So I'm going to copy and paste it right here. And let's take a look to see if I've got this correct. So x2 minus x1 in this sense. Alright, so of course I can make this a positive sign. I have to bring the negative sign inside the brackets. But I'll leave it as is and just change this to be 3 and this to be 1. Alright, I need to make sure that I've got all my brackets closed. Alright, I don't see any little red things right here. Of course I can suppress the output if I want, but I can also leave these here. Maybe I will suppress these, okay, with semicolons. Okay, I'll still keep the same time, so I'm going to turn off the force after 5 seconds. Alright, and I need to go back to here and see what else I need to do for my outputs. Well, I know that y out is going to be slightly different. Let me expand this out right here. Okay, and here's how I know it. When I run it right here, okay, oops, I have a little error here. Let's see if I need to fix some things up. Looks like it's a problem in this guy right here. Missing a multiplication sign. Oh, missing another one right here, looks like. Yep, it's from the same copy and paste I did before. Alright, so a bunch of things ran. I've got some interesting graphs, but that's not important yet. I want to take a look at my workspace right here. You'll notice then that y out is now, well, it's 4 columns. Okay, just like beforehand where we had 2 columns, now we have 4 states, and therefore we're going to have outputs that are referring to the profile of each one of these 4 different states. So I need to come in here and add additional states if I want to extract it out of y out. And I have x1, I've got v1, I've got x2, and I've got v2. And they are of course the first, the second, the third, and the fourth columns inside of that y out result that I've got. Alright, well, if I have 4 different states that I care about and I want to track, I should probably make my subplots a little bit bigger, or rather I should have more subplots. So I'm going to copy this whole set right here, have it be all in a line of 4 by 1. And the first one's going to be in the first spot, second, third, and fourth. And again, if you don't know how this works, do like a help subplot and it'll explain what these 3 different numbers mean. Alright, on top of that, time is always okay on the x-axis, but now on my y labels I need to change things. So I'm going to call this the x1 position. I'm going to call this the v1 velocity. I'm going to call this the x2 position, and I'm going to call this the v2 velocity. And these of course correspond with my sequence of states inside my state vector. Alright, things are looking a little bit better now. I'll go back to my command window. Alright, I'm going to hit run. Looks like there's a bunch of things going on, so I need to discuss this. An undefined function variable in x, line 33. Well, it looks like I forgot to change what I'm plotting. So up here, I set my variables, but no longer is x defined in this way, so I need to change this to x1, this to v1, this to x2, and this to v2. I will actually turn that back on to close all. All right, so now I've got a double mass system with 2 springs and 1 damper, and I've got my force that is being turned off at 5 seconds. Okay, so that's why it's kind of a weird thing right here happening. Let's start talking about this. Okay, so what happens when my force starts to increase? Well, if you recall from the image, so let me pull this up again. Okay, as force turns on, initially x2 is going to go up. Okay, because of that, there's going to be a force expressed by K2 to pull it back, but if it's pulling it back on this way, there's going to be an equal and opposite force pulling on x1, so x1 is also going to increase. And if x1 increases, well, both of these, the damper and the spring, are going to pull back on m1. Okay, so eventually we're going to have some sort of oscillating behavior between all of these different elements inside the system. Okay, let's go off and try to predict, or at least think about, what's going on right here. Well, initially everything is going to go up. We talked about how x2 increases in a positive direction, and therefore x1 increases in a positive direction, but at a certain point, okay, you reach where x2 has been kind of saturated, and K1 has been saturated, and K2 has been saturated, and so you're going to start having both these masses get pulled in the other direction. Okay, and so in fact the velocity is going to go negative at some point, and we're going to start to see this oscillating behavior, okay, where both of these masses are going to be at different locations at different times, and the spring lengths are going to be different because their positions are different. Now you notice then that right here at this magic point we kind of turn off the force, and so things start to maybe settle out. If we take a look at what happens over a longer period of time, let's see if things reach back towards that static equilibrium point. So we'll go back to MATLAB right here, and we'll increase our final time to 40. Okay, and then we'll take a look at the results here, and we can see that yes, it looks like the amplitude of the displacements are slowly weakening, and therefore it's oscillating at a much lower amplitude, and as a result it's slowly getting back to static equilibrium. Okay, let's try to find out where that is by increasing the time by much longer, and I'll do that by actually suppressing a whole bunch of data so we don't have to look at it on our screen. Alright, and then here's the graph after 400 seconds, and sure enough, right, all these elements are changing and oscillating for a while until the damper is able to dampen out all of those motions, and eventually we get back to a steady state, static equilibrium position with our springs. Now, let's see if that force, though, was on until, say, 50 seconds. Let's see how this thing changes. So I'll come in here, and I'll change my time from after 5 seconds, it's going to go to 0 after 50 seconds. All right. So this should be kind of insightful or kind of interesting to see, is that because you have a continual force for the first 50 seconds, there might be a different static equilibrium, okay, at a different displacement point than after we turn it off. Effectively, think of it this way, where I have gravity working for a little while, and then I turn gravity off, and so as a result, that displacement is going to change. But the static equilibrium is still going to exist under a constant force. And so the force due to gravity in a vertical sense is always on, and so we take the static equilibrium point about that point, which negates that. But in this case, we have a horizontal force, which we have all the time, and so the displacement would balance out that force for all time, except that then we remove it, we're going to go back to a static equilibrium that'll be different in terms of displacement. All right, so hopefully that little example will help you out with one of your homework problems. And now we're going to go off and do one more example in a rotational sense, and I'll move a little bit more quickly, but hopefully you'll be able to kind of see what I'm doing and how I'm applying ODE 45 to solving these problems. Okay, we're back discussing another system. In this particular case, it's the dynamometer. Can you recall that there were two plates that would rotate with respect to each other? This one was connected to a spring, a torsional spring right here, and it was going to turn a dial. And we had two position coordinates, theta 1 and theta 2, and of course we changed one to omega 1 because we actually care more about the angular velocity of this one, but we do care about the position of this one. We wrote up our equations in motion, and so up here we have our little equations of motion. Okay, they're not too bad, but we need to kind of talk about, well, how many degrees of freedom are there, and of course, what are the states? So we can start to identify some states. We know that this one might be a state, this one might be a state, and perhaps these two are states. Okay, but we'll try to figure out what we can do about those ones. And then, of course, we might have this one and theta 1 as well. All right, well, let's start taking a look at these equations. And what we'll do is we'll try to identify what the states are once we take it from the higher order term and isolate it. All right, so we're going to try to isolate the highest order term. In this particular case, it's going to be this guy right here. Okay, we'll do 1 over mass moment of inertia. And then we have that external torque, very similar to our external force in the previous examples. Then we have that viscous damping, fluid viscous damping in between the two plates, times omega 1 minus omega 2. And I usually do a lowercase omega, but in this case, hopefully it'll be obvious what we do. But when we go to MATLAB, I'll probably change it to a W or sorts. It kind of represents that omega. All right. Oops, this is a single dot. Okay, well, already we can ask ourselves, hey, you know what? Is this in state variable form? And I look on the right-hand side, and I don't see any first derivatives. And I only see, well, states, which might be these guys right here. Okay, external inputs and constant parameters right here. Okay, so already for free, I've got one of my state equations. Okay, the second one, let's see what happens next. I'll isolate it, and then we'll see. All right, well, it looks like over here, okay, I've got another state equation. Okay, well, because I've got some constant terms, some parameters, and I've got, hopefully, the remaining things are states. Okay, which what that tells me then is that I have some sort of other equation, okay, like this, which needs to have a dot equal to, well, omega 2. And these are my three state equations. Okay, why do I need this last one? Well, effectively, if I identify all these terms and I can classify them in the three categories of either being states, constants, or inputs, I need to have one more equation that satisfies the requirements of a state variable model. So at the end of the day then, I can have something like this. I have theta 2, omega 2, and omega 1. This all right here will be my state vector. And then I can have theta 2 dot, omega 2 dot, and omega 1 dot. Be my state derivatives. Okay, and now you can ask yourself, what about theta 1? Well, we can always add that if we wanted to. Okay, I don't see any theta 1s here, so it'll be a trivial equation very similar to this, but if we wanted to, we could also add it. So let's add it right now. Okay. And of course, we can add it to our state variables. Okay, we could add it down here, up above, or what have you. Now, the question though is, well, is it necessary? So yes, it's necessary, although if you recall, I only really care about the velocity of this domain. There's no sort of springs or torsional springs on this side, and so as you recall in a previous lecture, we talked about how y would my position vector actually be a velocity, an angular velocity, whereas this one I do care, and so I would have theta 2, or an angle directly. But it's always okay to carry more equations than you need to satisfy all the energy states of the system. But to remind yourself, or ourselves, you only need 3 equations, okay, because there's only going to be 3 types of energy that are independent from each other. There's of course the kinetic energy of this flywheel right here, there's the kinetic energy of this flywheel right here, there's the potential energy that can be stored inside of this spring. So 3 is enough, but 4 equations of motion are of course helpful if it helps you identify and understand how to set up the problem. So we're going to now go off into MATLAB and we'll see what happens when we try to do this system, and you'll see that the exact same thing exists for either 3 or 4 states in your state vector. All right, well the first thing of course is that I'm going to talk about these ones, okay, and I'm going to call now theta 1 and theta 2. Okay, then we'll call this one omega 1 and this one omega 2. We of course need to change these, and I'll put them in a different order. Okay, but here we now have our state vector. It's got 4 different states. Okay, and now all we need to do is go off and change our equations of motion. So we need to update some of these things because we have a J1 and a J2. Okay, and I'll go back to here and I'll talk about what the results are. So we had J1 being 0.2. We had J2 at 0.1. Okay, we only had 1 spring constant, so I'll move that right there. It was at 200 Newton meters now per radian. We had an M of 100 newtons meters. Now there's a moment arm for that. Of course, that's where we get the units there. And then B was set at 1. And watch your units, of course, but it'll be Newton meter seconds per radian on that. Okay. We've got now our constants. Okay. We need to talk about our inputs. Well, that's M. Let's say that we forget about this. So we'll just remove it entirely. It's going to be a constant moment at 100 Newton meters the whole time. Okay. And now we need to update these equations right here. All right. Well, let's do the first one, but let's see what we had before. The first one was theta 1. Okay, that was our first state in the state vector, and that's actually this last equation right here. And it's going to be equal to omega 1. So in fact, this line right here is correct. Okay. The next one we have is, well, omega 1. Well, omega 1 dot, of course, is going to be the angular acceleration about 1, and that's given by this first equation up here. Okay, so let's take some time and we will write that one out. Well, we have 1 over J1 right there. Okay, there's going to be that moment, external moment applied to it, of course. We're going to have a damping term in between the 2 plates. Okay, so I'll get rid of all these, and then we'll talk about what goes inside this little term right here. Well, it's omega 1, okay? And that, of course, was, well, itself. So that's going to be x2. Just like this guy right here is the same as this guy right here. Minus omega 2. Well, omega 2, we put it as fourth right here. So we'll have it as x fourth. Or x4 right there. Alright, so that takes care of that equation. Now we'll do the third element. Let's talk about the third element. The third element was theta 2. Okay, well, that was also a really easy question right there. Theta 2. If I want to get the derivative, I just have to make it equal to omega 2, which is x4 again. And then all I have to do is the final last question, the one that I haven't used, which is this guy. So we got J2 right here. I'm going to copy and paste this over. It'll save a little bit of time. Okay. Let's review if it's the same. It's at theta 1, which is x2. Sorry, omega 1, which is x2, minus omega 2, which is x4. Okay. Plus k times, I've got a little bit of theta 2 right here. Well, which term refers to theta 2? Let's go back and we'll find it. Oh yeah, theta 2 is actually x3. So I need to multiply that by x3 right there. And I've got my 4 equations of motion. Okay. And of course, everything on the right-hand side is either constant terms, external forces or moments, or state derivatives. Sorry, not state derivatives, states from the state vector. All right. Well, I've got 4 of these, so let me go off and check to see if everything's correct. I should probably do this not position now, but we'll call it theta 1, theta 2, omega 1, and omega 2. And of course I should probably change these as well, so I'll do theta 1, omega 1, theta 2, omega 2. Theta 1, omega 1, theta 2, omega 2. Alright, let me decrease this down back to 40 seconds from the previous example, and then let's see. So I made a little error in my equations of motion. I need to come back and change this guy. So I need to make that into a negative. Let me just check these other ones. Isolate that guy. Isolate that guy. All right. Then I'll go back to my MATLAB right here. Okay, I've corrected it now. Okay, let me just confirm that that was not correct from beforehand. And I've got a negative sign right there. Let me just make sure everything's correct. And let's see now if this makes sense. All right, so I'm getting some results now. Okay. And now we need to kind of explore what's going on right here. Well, it looks like that after about, well, I don't know, what is it, 2 seconds, I've reached a steady state. Okay, so I'm going to home in on just the first 2 seconds. Okay. And we're going to take a look at these and kind of think about what's going on right here. Well, theta 1, if you recall, we weren't so sure that we needed it. Okay. But we did think that omega is going to be important. So what happens though is that as the velocity increases, okay, we're going to reach a steady state velocity because the velocity on that first flywheel is going to be, well, now we know, about 100. Okay. Theta 2, right, it's also going to reach some sort of max value, and there's going to be some sort of transience period up until we reach that steady state point. And then with omega 2 itself, okay, it's always going to be positive, but it seems to kind of bounce back and forth from 0 up to that value. And again, like it said, it takes about 2 seconds to have that reading. So this dynamometer seems to have like a response time of approximately about 2 seconds before you should probably take a measurement on the dial. Based upon the spring constant and the damping factor, it's going to take some time to reach steady state. Now the question, of course, is that this theta 1 right here, is it useful or not? Okay. Well, it seems to keep on increasing, and if this is in radians, okay, what's really going on right here? Well, it just tells you that the motor, or the first flywheel, is continually increasing in a positive direction with respect to the positive coordinate. The meaning, it's not as meaningful because 150 radians, as you know, isn't nearly as important as, for example, the velocity in this case. All right, so can we do the same sort of thing without having this state vector? Sure. Let's go off and try to remove this as one of our states. We don't care about then theta. Okay. We don't care about theta. All right, so I'll remove those two. We don't care about theta. Okay, which means there's 3 other ones that we do need to care about. Oops. 1, 2, and 3. Okay, we don't need to care about theta, so I'll just suppress that entirely for the time being. Let's go up to the equations of motion, and we don't really care about theta. Okay, and why is that? Well, because these other 3 equations never use x1. Okay, so we do need to update some things. So for example, 2's become 1's, 3's become 2's, and 4 become 3's. 4 become 3's, 4 become 3's, 3's become 2's, and 2's become 1's. Okay, now we have 3 equations in our state variable form. We're going to come in here and let's see what the results are. Yeah, they're identical. Okay, in the sense that yes, for free we can track theta 1, but it's not nearly as important as the 3 most important states. Why is that? Well, because kinetic energy of the first flywheel is demonstrated right here. Potential energy is demonstrated in this state variable. And kinetic energy is demonstrated in this other flywheel, respectively. Of course, we can always track theta. We can always track more states than what we want. But in this particular example, the dynamometer, you can get away with only having 3 states. That being said, a lot of people will always just have 2 states, the position and the velocity, or the angle and the angular velocity for every single position coordinate. Okay, and now for our last example for the lecture, we're going to talk a little bit about taking this system. I've already, again, given you the equations of motion up here. And we're going to see what does it take to kind of figure out what the dynamics of this system are using ODE 45. All right, well, as before, we need to isolate. Let's see if I can. We need to isolate this guy and this guy, and then try to discover what the state variables are from looking at the equations of motion. Well, let's write it out. So we got x dot. We know that we're going to have 1 over m. And that's going to be multiplied by all these other guys that we're going to bring over to the left-hand side. So we're going to have k1 x minus r theta. Okay. You should notice that x is with respect to the middle of the cylinder. There's x1 right here, and x2, and there's a theta. So it looks like there's 4 position coordinates, but we're going to see how few we can get down to for our different states. Oops. That's going to be a minus. I think that's what I did last time. We have x plus r theta minus x0t. All right. So we know that, of course, we have to get this down to a single derivative. So we've done this before. We can have x dot equal to v. Okay, that's all good. So we've got one equation with a first order derivative. This one right here now needs to be updated to be v dot equals, well, all this stuff. So I'm going to go off and grab it. But now let's talk about these things. So k1 is a constant, that's fine, that can exist there. X can be a state variable, it's going to be right there. Okay, r is going to be a constant, that's fine. We have theta, so theta is probably going to be a state variable. Why is that? Well, because of course it can change over time, and of course it can't be classified as an input or a parameter. We have k2, we have x again, r theta, and we have this guy right here, which can be viewed as an input, not an input force or an input moment, but a position input on the other side of a spring, which effectively is going to come out to be some sort of impact of a spring force right here. All right, so if we have this theta, then we know there's going to be another equation that will have to have, well, theta dot somehow. Well, it's going to be this one right here. So we'll start first of all by doing theta double dot, and we'll do the same sort of process by isolating it, the highest order term. Let me just check my math here. Hopefully it's all okay. All right. And then, of course, like we did before, okay, we know that theta dot is going to equal, well, omega. And so then we have to go back in and we replace omega dot equals, well, all this stuff right here. And now we can ask ourselves, let's check all these equations and see if we have them as parameters right here, 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 and there. We've got our state vectors because we know we can reduce the dots and see the states right here. Okay, we have x, which is also a state, and then everything else is going to be a state or not. Okay, so let's go and take a look at our equations that'll satisfy the state variable mode. These two, this one, and this one. So we're going to have 4 of them. Let's go off to MATLAB and let's see what happens to this particular dynamic system. Well, I like to start by defining what my states are. So in this case, I'm going to change this to be x1, and we'll change this to be v1. We'll change this to theta and omega. Those are going to be our 4 states. Okay, and of course you can see that this is a state derivative, but the value or the vector without those dots is going to be the state vector. And then of course we need to change this up here of x, v, theta, and omega. We'll see that everything starts up at 0. There are my 4 initial conditions. Here's my state vector. Okay, I can turn back on because I know I'm going to have outputs of all 4 of them. So I'll make this x and v, theta, and omega. And I'll change all of these as well. I had an X, I have a V, I have a theta, and omega. I'll change the labels really quick. Okay, and I need to realign all of my outputs from the previous example, 1, 2, 3, and 4. All right, I still have this as identical. I'll keep it at, well, maybe I'll do 10 seconds here for a little bit, and then I can change that later on. And then I need to go off and change my equations of motion. Well, I'll keep J as 0.2 and change where it occurs. Okay, and I need to realign these 1, 2, 3, and 4. All right, and so now let's start talking about, well, the equations of motion. Well, this first one is often similar. So x dot equals v. Okay, since that is referring to my first state in my vector, I know that x dot is going to be equal to the second state in my state vector. That's going to be the same. I can come down here and do the same sort of thing with theta. Now I just need to place these inside the form. So I do need a mass right here, and we can probably figure out what the mass is, but I need to assign some sort of r. Okay, so let's say r is 2 meters. Let's say m is 10 kilograms, which means then that j is not going to be known, but we have to calculate it. It's going to be 0.5 times m times r squared. We've got m, r, and j now, at least examples. Okay, which now means we can go in here and change 1 over m times everything in that bracket right here. I've got a negative k, 1. Oh, in this case we have 2k, so we need to come in here and make some spring constants. I'll make the one on the left half as stiff as the one on the right. So k1, then we've got a little kinematic relationship right here. Okay, so it's x minus r times theta. Well, let's talk about what r is. R is known, that's a constant. What is theta? Well, theta is one of our state variables. It's actually x3. So we're going to come in here and make this into be x3. All right, and then what's this x right here? Well, this x right here, okay, is actually one of our state variables, but it's actually the first one. Okay, so we need to come in here and do this x1 right there. And so now you can see that this right here multiplied by k1, I won't make that mistake again, okay, is going to be that first term inside this equation right here. All right, now we'll do the other one. So it's also going to be something similar. I'm going to copy and paste this, and we'll try to update it here accordingly. We know it's going to be minus k2. Okay, there's going to be an x1 for the r, or rather, there's going to be an x1 for the x. There's going to be an r times a theta. In this case, it's going to be a plus, so let's come in here and make this a plus. And then after that product, we're also going to subtract x of t. Okay, I'm going to call it x0, or x, actually not, let's do that, xo, right there. Okay, and it's going to be like our forces, but it's not going to be necessarily a function of time. It's just going to have a value that we need to compute right here. So let's say it changes with time. So given our time, it will be twice as fast. Okay. So at time equals 0, x0 equals 0, and at time equals 1, well then x0t is going to equal 2, and so on and so forth. And we'll play with this in a second. We'll actually also make it wall at 0 for a bit. Okay, so we've got two equations, and let's do the last one right here. Okay, there's something relatively similar except with the moment arm. So k1 times r theta minus x. Okay, now so I'm flipping that around. And then the exact same value for K2. So I'm going to come in here, and I need to check my parentheses. Looks like that is closed, that is closed, that is closed. And I'll suppress those two values. Okay, and if I've done everything correct, then hopefully this little thingamajig will be able to be analyzed dynamically through numerical solvers of ODE45. Let's see how close I was. All right. Well, let's talk about this. So first of all, we have x, okay? It seems to always be increasing more and more, okay? That's this point right here. It seems to always be going up. And it may be because this point is always going up. Okay, the velocity of this generally is up at about 1. Okay, now why is that? Well, because we're kind of increasing it over time. Okay, with respect to this x over t, we'll make that to be 0 here in a second. Theta itself is also increasing more and more. What does this tell you? Well, that means that this little cylinder is actually rotating in an anti-clockwise way for all 10 seconds of our simulation. Okay, and then the omega, okay, the angular velocity is also kind of bouncing up and down a little bit as the two springs are interacting with this particular thingamajig. All right, so that's when this xt is kind of moving up with respect to time. Let's just say that it moves up with respect to time for only the first couple of seconds. Well, we can come in here, okay, and then we say if time is greater than, say, 5 seconds, well, xo is going to be equal to 0. Let's come in here and we'll rerun it. All right. So we have something very similar in the sense that we have x always increasing for a while, okay. We had this velocity, and of course we can zoom in on it. It's going to be the same sort of thing. It was varying. And then we also had theta, which was always increasing. It was always rotating anti-clockwise. And omega, but then as soon as we turn it off, okay, we have this little system where it is going to continually vibrate or oscillate because we have some sort of energy inside the system. Now, what happens if we start with 0 and keep it at 0 the whole time? So x0 is going to be a wall. Well, nothing exciting at all. Well, why is that? Well, because we had no sort of external forces, okay, that it started at static equilibrium because that's what we assumed, because there was no gravity inside any of our equations of motion. And so without any sort of injected force or positions or moments, this thingamajig is going to stay stationary for the full time. And you can do that for other examples too, if you followed along in the MATLAB examples. All right. Well, I've shown you a couple examples of how to use ODE45. I've tried to walk through this process of putting in the equations of motion and converting them into state variable form by making sure that you have something on the left-hand side that is a vector of all the derivatives of the states, which of course is then going to give you the state vector. And then everything on the right-hand side has to be the states themselves, constant terms, or inputs in some way. So scrolling back up to the top here, just to kind of finish off the conversation again, the state variable form is this guy right here, where effectively there is a vector of first derivatives on the left-hand side, and then a whole bunch of functions that make use of the state vector elements right here, and all the other stuff, constant terms, forces, moments, inputs, external things. And if you have that, you have your state variable form, and then it's very easy to go back to MATLAB and convert it, because using ODE45, it expects you to give this result and in this format, and then it's going to take care of the Euler's method or Hoynes method or Runge-Kutta method, and in this particular case the OD45 method is a fourth order Runge-Kutta method, and so you'll be very accurate and it's very, very fast. All right, we'll talk to you on Monday. Hopefully this kind of helps you and walks you through a little bit of OD45 and some state variable forms. Please practice it, and good luck with your homework.